Thanks, Armageddon. Well, I'm glad to see you here today, and I'm pleased to be here. Just a bit of additional background for me. My training initially was as a lawyer. I spent 17 years with a public engineering company doing mergers and acquisitions. So I don't have a lot of direct construction engineering experience. I'm learning as I go. I've been at Almeida now since 2011, so I've had a few years of practice working on these things, and I have a pretty solid understanding of how it all works. If the questions get too technical, I have a lot of friends in our company and our engineering team that I'd be happy to connect with you to help answer some of those questions. So today, just a quick overview of where we're headed. We'd like to talk about helical piles, environmental and economic advantages, what makes us special in the piling industry, and why do we think that helical piles are a growing way of the future. Some different applications, things that we think about when we're designing piles, and then questions and answers. Having said all of that, if you have questions along the way, this is a small group. I'd be happy to stop and talk about any issue at any point in time. And at the end of the presentation, after the questions, I've got some additional slides that we could look at, some additional types of projects and applications if time permits. So just to make sure that we're all on the same page, typical helical pile, the design elements of this pile that are important. The helix spacing is critical. The helixes have to be matched in their spacing so that the distance between the leading edges of the helixes is a multiple of the pitch of the helix, and that way both helixes follow the same path into the soil as they go. You'll see all kinds of different end treatments at the bottom. We use a 45-degree end profile. It allows us to point the pile into the ground. It's an easy and economic cut and allows us to point into the ground. For targeting. Some people put a conical shape on the end so that the point is in the center of the pile shaft. We don't find that to be necessary because the pile moves as it goes into the ground, and we find that we can target quite well with adjustments at the install as the install progresses. And then just a little bit about how the pile works and where it takes its bearing capacity. So you can see in a compression state, the capacity comes from the bearing loads, the end bearing loads of each of the helixes, plus the frictional load on the pile shaft. And in a tension setup, it's the pile shaft and the uplift resistance from the individual helixes. So that's one model. That's the individual bearing method for individual helixes. And then for the cylindrical shear model, it's basically the concept is the same as the prior method, except that we consider this as a soil plug that forms between the two helixes. So instead of getting individual bearing from each helix, you get the cylindrical shear resistance of that soil plug. It's kind of like creating a bell pile at the bottom or something to resist the uplift that's larger than the shaft diameter. So just a little background about Almeida. Been in business since 1991. We were the leaders in the growth of the screw pile industry in Alberta. The industry really grew around the oil and gas business that serviced or that exists in Alberta. And first conventional oil and gas, pump jacks, drill rigs, that sort of thing, and has since moved into the oil sands. And the move into the oil sands allowed for a lot of research and development into larger scale piles. We deliver our piles in a couple of ways. We have, for the larger piles, we do the design, fabrication, and install. For smaller piles, we will do some of the installation, but we rely on a network of external installers. So those would be individuals, some of them in the construction or the pile business exclusively. Some of them are landscapers or other construction people with small equipment that can be adapted to install screw piles. Through that group, we do about 40,000 piles a year of all different sizes. Our employee numbers fluctuate. We've been as high as 300, down as low as 100. 200 is a reasonable estimate for now. I think we're a little under that, given the state of affairs in Alberta these days. And we've had a history of research. We were the first helical piling company to have an in-house engineer. We've had a partnership with the University of Alberta since our inception. We were a founding member of the Institute of Helical Pile Engineering, which was and is an institute that includes the leading screw pile companies from around the world. So we have Screwfast in the UK, Piletech in New Zealand, EZAT in Japan, which are the primary jurisdictions that use screw piles around the world on a large scale. The only area that we haven't covered off right now is Brazil, where there's a fair bit of screw pile work being done. We don't have a member of the institute there as of yet. So this video will show you just a little bit about our company and the life of a screw pile.
It begins with an inquiry, a set of specific demands, needs, another client, another challenge. Almita Piling's fully integrated design, fabrication, and installation practices have set us apart to become one of Canada's leading manufacturers of helical screw piles. Located in Western Canada, we service a vast array of industries, from oil and gas, power transmission and distribution, to industrial and commercial construction. Our true helix design, much like a thread on a screw, allots for minimal soil disturbance, meaning a stronger, more stable pile versus traditional duck-built screw piles. Our expansive team of employees and years of accumulated field research stemming from our partnerships with universities means the journey of a helical pile is a comprehensive display of collaboration, precision, and hard work. When a client makes that initial inquiry, our sales team, collaborating with our engineering department, can provide the most accurate quote possible. Once the order is placed, our engineering department of geotechnical and structural engineers is mobilized. Drawing from our extensive industry experience and using Almeida's proprietary analysis software, our engineering department takes our clients' foundation needs from concept to production. Overseeing this process are the project management professionals. They ensure the successful execution, delivery, and completion of every project, and are just one more reason Almeida stands out from its competition. Safety is paramount at Almeida. Working within strict safe work practices, the fabrication team brings the helical screw pile to life in one of the world's most advanced screw pile fabrication facilities. When the helixes are ready to be attached, a robotic welding arm automates the process, guaranteeing an exact, high-quality weld. Each screw pile is equipped with a true helix shape, ensuring a 90-degree angle between the helix and any point of the shaft. The screw pile is completed and ready to be shipped. Once packaged and loaded for transportation, the installation team is ready to get it done. Almita Piling uses some of the largest drive heads in the world, with over 250,000 foot-pounds of torque. And our helical screw piles can be installed in uneven terrain from most angles and in nearly all climates. The piles can be safely and easily removed and reused again, making our screw piles a greener, economical solution. From here, the piles have reached the end of their journey. It's a job well done, and the Almeida team is proud of it. For the screw piles, their job has just begun. It's time to head back safely, ready for the next challenge. Almita Piling, providing complete support.
So it's a little self-promoting, but it's a really good overview of the life of a pile. The Upfront Design, for us, fabrication is a high volume process. We do a lot of piles every year. You'll find in the industry everything from individual welders building these things in their garage all the way up to full-scale production like we have. A lot of what you'll see in the industry is that it is commercializing, it is getting more competitive, and certainly in Alberta, it's one of the most competitive screw pile markets in the world. It's caused us to focus heavily on bringing the cost of that entire process down. So a lot of that is scale of what we're working on, and as long as you can feed the machine at that scale, it's a very economic way to work, to the point where we can now produce high volume screw piles at a significantly lower cost than the individuals working in their own little shop. So it's quite interesting. We actually supply those piles across Canada. We've had people drive from Ontario to Alberta to pick up piles. And so it really is, it shows that the local production of those can't compete with the cost that we can provide them. We work primarily, Ponoka is a small town between Edmonton and Calgary. It's where the company was founded. It's where our production facility is. It's a low-cost environment. It's a farming community. It's serviced by a lot of farm kids and hardworking people from rural Alberta. Edmonton and Calgary are our primary sales centers. Calgary has a lot of oil and gas customers there, based there, so we work there. Edmonton is where I'm from, and a lot of our leadership team is there. It's the closest large center and airport to Ponoka, so we have a corporate base there. Saskatoon is newer for us. We've had that location for a few years as we move eastward. It does a lot of electrical transmission work, primarily for Sask Power, and then serves all of Saskatchewan there. One of the exciting things for me is that within 30 days, we're just working on the finishing touches, we'll have a location in Guelph. So just down the road, we'll be neighbors. I was out there yesterday and I see that we've got a truck and a piece of equipment here already, so that's very exciting for me, and we'll be able to manufacture piles here in Ontario as well. So we're taking the expertise that we have in Alberta, bringing it to Ontario. The primary focus right now in Ontario is solar farms, and so we'll be pursuing that market. But there's also a big electrical infrastructure build coming in Ontario, and we're very well established in that industry, and we have great partners, and we look to facilitate that build as well. So here are the industries, and a few notable project pictures beside them. But power transmission and distribution, whether it's renewable, in the form of solar, wind, we do a lot of work there. The picture that you see there actually was one of the first solar farms that we ever did. It was in Arnprior, Ontario. It was quite a large project, and done. We actually subcontracted the fabrication of the piles here because of the regulatory requirements, and I'll talk a little bit more about that project. Wind turbine foundations, we don't do as many of those. Those are large, high-scale, high-capacity foundations, but we do have a methodology, and it continues to evolve, so we will be larger in that market in the coming days. Transmission towers and power pole bases are a very big component of our business. And again, back to simple terms so that I can understand things, when you get a big transmission tower and it wants to tilt over one way or the other, two legs are going up and two legs are going down in order to accomplish that. And that's one of the key things about screw piles, is that their resistance to uplift gives them a significant advantage over every other piling method. When you think about a driven pile, a caisson, that resistance to uplift allows you to use a significantly smaller pile to achieve the same resistance. Oil and gas is important, particularly in Alberta. We do a lot of the oil sands mining projects, the SAGD facilities where they're not mining, but they still have the wellheads and all of the gathering lines and all of those sorts of things. Central processing facilities, and all of the other site infrastructure. These are large remote construction sites. It's difficult to get in with concrete. And harsh weather conditions, so concrete isn't as useful as it is in other environments. Lots of oil field pump jacks, batteries, and then on pipelines we have a lot of ancillary services that we can do, whether it's the pipelines themselves, where they're above ground, anchor blocks, pump stations. So we have a big application there. The other application that is available, we don't do it as often, but it's buoyancy control. So we'll do that as well in the pipeline sector. A big market for us now, and really outside of Alberta, you get into this market a lot more. You don't have that same oil field place to play. So the commercial infrastructure is very important, and it's a big place for us to play. Work camps and office trailer structures, any sort of remote construction site. But commercial and industrial buildings, you'll see them all over the place, but anything up to about a 4-story building has a practical application for screw piles. Streetlight and sign bases, again, very useful. Looking out the window, we see the new LRT going in. That's a perfect application. The piles can go in the ground. They're removable, reusable, so if you want to relocate the infrastructure, it's easy to do, and they go in very quickly. We also do some bridge work. We can do overnight bridge replacements when you want to replace a small rural bridge. Friday night, the old bridge comes out, the new foundations go in. Over the weekend, the new bridge deck is prefabricated and set on. So in a rural environment, particularly where you don't have convenient access to detours, we can do very fast bridge replacements. So the advantages, and the advantages for a screw pile or for a helical pile, there are many, and when we try to look at the overall advantage, it comes from a number of different places. So there's not one particular overwhelming advantage that you say, gee, here's why screw piles make sense for our projects. The difference comes in a whole bunch of different places. And just to pick a few, the cost-effective side of things, you think about using less material. There is a fabrication component, so compared to a driven pile, it'll be a little bit more expensive, but we use about half the steel on the pile shaft compared to a driven pile to achieve a similar capacity. So that's kind of puts them on an even footing. But then when you add in the number of trucks that you're carrying half the steel, so you have half the trucks. The speed of installation, so anything that you do along the life of a pile to compress that, all of the surrounding support infrastructure only needs to be deployed for a shorter period of time, so you get a savings there. When you install, we're very agile with our equipment. We use track-mounted excavators that move around very quickly. When you go to install a pile, the machine is set on site and it's ready to go. There's no mast to raise like there is on a driven pile rig, no concrete setup, no pumper trucks, all of those sorts of things. So we're very efficient and we're compact in our delivery. A lot of our, in the municipal setting, in more congested areas, a lot of it is done with truck-mounted boom trucks. So you drive up with your transport truck that has the boom on the back of it. It pulls the trailer full of piles. So it's a one unit driving along and can actually install from the roadside in many cases. The speed of installation, with that design, it advances every rotation of that drive head, advances the pile between 3 and 6 inches, depending on the pitch of the helix. So it goes in very quickly. And then the other notable thing with a comparison with driven piles frequently have to be retapped, which means coming back, setting up the rig again, and tapping the pile. We don't do that nearly as often, but when we do have to retorque a pile, if there's something on the install that didn't go quite as expected, we may have to come back and retorque the pile. But again, the agility of our machines is so fast that those retorques are very efficient. The ability or the adaptability of the system. So when you look at the install, any angle of battered install is available to us. And that's important because the most efficient plane for the pile to work in, compression is obviously its most efficient plane, but tension is the second most efficient plane. So if you can line up the pile to directly resist the load that's going to be applied to it, you can you can achieve your capacity with a smaller pile. So we can get all the way up to horizontal with our equipment, and we do that on retaining walls to resist in the plane of the load that's going to, or to counteract the plane of the load that's going to be applied. Soil conditions, if they get too hard, we can't install the piles and you have to go to a different piling method. But that's true of all of the piling methods, or the traditional piling methods, whether it's driven or concrete. If you hit rock, you either have to use the rock as your foundation or you have to drill through it. And any weather condition, and that's important. We can easily penetrate frost. Sometimes we pre-drill through frost to get through the frost layer. But for our work in northern Alberta, a lot of the times we're piling right through the frost without any difficulty. So we can work year-round. We don't shut down for a winter construction season. I know in Ontario, concrete comes to an end. Concrete use comes to an end sort of the end of October, November, and is shut down for 3 or 4 months until the weather returns. Screw piles can be used year-round. And in fact, winter is our busiest season in Alberta. And they're usable right away. There's no curing time like there is for concrete. So again, all of those, they're just a number of little things, but they all come together to create a very economic solution. The other is just the safety of it. When you think about that install, we're not dropping hammers and pounding a pile and having that explosive force. It's a high force, but it's relatively gentle in its application. It's very controllable. And you'll see in the video, I think you saw the install operator, or the ground crew member, checking for the trueness of the installation of the pile, standing beside it as it rotates around, and it goes about 6 revolutions per minute coming out of those drive heads. And just a bit of a direct comparison against concrete. Most importantly, the idea when you're not drilling, there's no tailings. And it's important because you don't have to remove the tailings, you don't have to disturb the soil. We did a project in New Jersey where the ownership of the tailings was a significant issue, and the screw pile as a foundation method was a big part of that solution. It alleviated the need for somebody to take ownership and remediation responsibility for the tailings. No concrete curing, no assembly of rebar, anchor bolts, liners. We can go into very wet conditions, no weather restrictions, and we do work with a very small crew. So concrete has its application. It's certainly a very economic solution in the right environment. If you're doing a lot of it, if you're doing it in an environment where the concrete is closely available, if the weather conditions match up, and if your labor costs are low, then it can be a very viable solution. And I think that's something to remember, that screw piles won't replace everything. They have their time, they have their place. It's important to know, though, that they're a viable alternative and probably a preferred alternative in a number of applications. The other thing that we're seeing as the industry evolves is that the competitiveness of screw piles against other piling methods is increasing. Concrete piles have been around for a long time, driven piles have been around for a long time. Screw piles are relatively new, and the companies that provide them are continuing to learn about efficiency and trying to drive themselves into that place of competitiveness in the areas where they're kind of on the edge now. And we're seeing that in Alberta in particular in the commercial sector, where screw piles have traditionally struggled to gain traction. But now with the companies focused heavily on their competitiveness because of the price of oil, we're seeing that they're displacing a number of primarily driven piles in commercial construction applications and in some cases concrete. Just as a comparison to the driven piles, when you visualize a work site, the congestion on a work site is important. When you think about the safety zone of a piling rig, so every piling rig has a safety zone. Basically take the height of the rig, drop it on its side, and draw that circle, and that's kind of where you have to protect, is anything that falls off from that height could come out to that area. So you have that safety zone. So a driven pile rig will have a large safety zone. A helical pile rig is only the length of the pile, so there's no hammer swing space. So we're typically 30 to 40 feet, and that's the circle that we have. So it's a very compact work zone, which is great for congested work sites. So again, it works well in commercial construction where everything is sort of working in close quarters. But on large congested sites like up in the oil sands, we see that as well, where our work footprint is much smaller. Driven piles usually have to go much deeper, and we spoke already about the agility of a tracked excavator or a mounted truck versus a driven pile rig, which are typically slower to move and slower to set up. One of the key things about screw piles is the noise pollution. We just did a project in Edmonton. It was the funicular lift down the river valley, and there were a couple of elements in that project that allowed us to be more competitive than driven piles. One is we were right below the Hotel McDonald, the Fairmont Hotel, where the concern of, I don't know if we're good. I'm just,
don't click on it.
just right there?
Okay, cancel it again.
There we go, okay. We were just below the Hotel McDonald, and one of the challenges was you can't have the hammer noise starting early in the morning and upset the hotel guests. Screw piles worked well for that. We have, it's kind of like the noise of traffic. When the excavator revs up to run the drive, it does, but it runs at a constant speed. So it's kind of like a truck going by. It's background noise, and it was fine for the hotel. It worked really well. The other thing that really did well for us on that project was it's on an incline in a river valley, which is a protected environment, and we didn't need a level working surface to run our excavator. So we actually, they built an access road straight up the river valley. It's quite a steep incline. Our operators took pleasure in driving the equipment up the hill. They thought that was a good challenge. And it's interesting, you can do it safely by extending the boom below the machine, so you kind of got an anchor out there so it can't tip or fall. We were able to safely get our equipment up there. We actually used a series of excavators to sling the piles up, so one would pick it up, move it up, and they would get it up to, the biggest chain was 3 excavators in a row just to move the piles up the hill. install, and away we go. Would have been impossible to do with a driven pile rig. First, just getting it to the install location, creating a level platform for it to work from would be very challenging. Speed of install is important. And the other thing is reclamation. So screw piles are removable. They're removable, and as long as they aren't damaged on the installation, if they hit rocks and cobbles and that sort of thing, they can get bent, and you might not reuse them. But more often, you pull them out, they look like they're a little dirty, but they look like they did when they were first put in. And that's, for lots of applications, they're reusable in that fashion. Particularly important for us, again, on the oil sand sites. When you go to reclaim an oil sand site, the traditional practice has been to sort of excavate a driven pile, cut it off, bury it, and call it done. For us, we can actually remove it. So first of all, cleaning up the space is important for us. But second of all, the ability to reuse, recycle that pile is important. Smaller crews and less material. Again, all very important from an environmental perspective. We're using less material, we're impacting the environment less in our process, and then anytime you can reuse, recycle. Armageddon.
Jeff, I have a quick question.
Sure.
When it comes to geothermal energy piles, which one is more preferable? Like you could use either of them, screw piles as well as driven piles?
I don't know the answer to that. We don't have a lot of experience in geothermal piling, but I'll tell you a couple things that come to mind. Driven piles are deeper. So to the extent depth is your constraining factor, driven piles will be better. The challenge will be that if you're going to put something inside of those piles, those driven piles, and then pound it, you have to make sure you don't disrupt whatever it is you've got in the piles. So that's one challenge. But it's certainly an opportunity, or install after the pile is installed. Screw piles will go in more gently, but they won't go as deep. So it is an interesting question. If screw piles in the fashion that they're intended to be used provide sufficient geothermal access, then they'll be fine. But I don't know for sure which method is going to be better for that application. As you and I spoke this morning, we are seeing geothermal piles in the US on screw piles, and so somebody thinks it's a good idea. I think it's a good idea for all of the sustainability reasons that otherwise exist with screw piles to be able to put it in. And again, if there's a cost benefit or a cost savings on the screw piles, it may be that you could use more screw piles around a site, get more surface area available for the geothermal piles, and have access and economically efficient access that way. It's possible. I don't have a great answer though. We'll figure that out though. I look forward to that. Yeah. Okay. Oh, it's moving. So some different applications for screw piles, areas where we've used them successfully. This is Armpire. We talked about it previously. You can see this was a big project. It was 26,000 piles, 5 installation crews. Each crew was doing about 70 piles a day. That's fast. We peaked out. I think our fastest crew did about 115 piles in a day. Some very skilled operators. And very competitive operators. There were no safety incidents, so that's always a test for us is how is the safety. But you can see the efficiency of this. These are very small piles. They're easy to handle. In some cases, they're handled just by hand when they're pinning them up. The equipment is small. The footprint is small. We can have 5 of those guys moving around a site relatively effectively. They don't have big footprints on their work area. That's one kind of installation, and that's all about installation speed. So you park the excavator in one place and you put in as many piles as you can without moving the excavator. And then you move to the next place and you keep going. It's very much a logistics exercise. And so a lot of that becomes how fast does the pile go in the ground? And that's one kind of project that we do. This is a Monopole Tower base, and so we talked a little bit about, we do a lot more transmission towers this way, but this is the same application for a wind turbine. And what it is, it's a combined piling system. So you can see in the first picture, screw piles have gone into the ground. They've got a cap with a rebar extension. The rebar gets built into a cage with a steel frame to accommodate the base of the monopole, and then the whole thing is cased in concrete. So you get the screw pile foundation at the bottom. It holds the concrete in place. The concrete serves the purpose of dampening load. It also has bearing capacity on it, and just the weight of the concrete casing adds to it as well. So that's a combined solution. It lessens the amount of concrete otherwise needed for those foundations by somewhere between 1/2 and 2/3. So it's an efficient use of screw piles to supplement the concrete method, and it's I think going to be the right solution for wind turbines, again on a significantly larger scale. Transmission line bucket piles. This is an interesting application. You can see a few different pictures. So this is the pile has a bucket at the top with a smaller shaft and the helixes down at the bottom. When that pile goes into the ground, you're basically creating a socket in the soft ground, drop the pile into it, fill it with gravel, and you end up with a finished product that looks something like that. They've got a little gravel spill there, but that raised pile protects against rodents, ants, and other things that can go after the wooden pole, but also gives it a lot of rigidity in otherwise soft ground taken from the more stable ground below. We see a lot of that application in areas where there's sort of wetlands, peat bogs, that sort of thing. I think Northern Ontario has a lot of those characteristics. Northern Alberta certainly does. Streetlight bases. We see a lot of this application in small towns, but it's also applicable. This is the kind of application for LRT lines, for railway lines. The piles are a little bit shorter. They don't bear a lot of load above the surface, but they perform an important function. You can see that they've got channels cut out within the pile for the electrical cabling that has to attach to the lighting system that goes on it. And in this case, and in many of the transportation applications, there's a breakaway system in there as well for a safety purpose. So the pile goes in the ground, and then the breakaway system goes on the cap, and then the light post goes on top of that. We've done a number of comparison studies. In the city of Edmonton, they like concrete foundations for their streetlights. And the reason that they give us is they can put the concrete in, then they grind it level, they put the light on, and when you finish your project, the lights line up very nicely. We're not quite as precise with the screw pile, so the lineup is pretty good, but it's not as perfect as it is on concrete. The interesting thing, though, is you go through 3 Edmonton winters and you come back and look at that same line, and the concrete light posts are nowhere near in line anymore. Over time, with the shallow foundation of concrete, the freeze and thaw cycle and everything moves. The screw piles will hold their form because we get the helixes down under the frost level, so that the frost doesn't jack on the screw pile, and they hold their position much better. So it's very efficient, and again, the removability for those types of applications are critical. We have a lot of projects in Edmonton where they built sidewalks with streetlights in them. Now they're converting everything to give it more access for cycling and mixed use functions. So a lot of projects where they're taking the streetlights out, moving them over 3 feet, putting them back in the ground. If they'd been on screw piles, it would have been unbolt, raise it out, move it over, put it back in. Instead, they've had to dig out all of the concrete foundations. Railways, we've done one of these projects here in Ontario for CP. We've done a number in Alberta. The railway business is on the rise, certainly crude by rail, a lot of oil shipped on rail lines these days. And what happens in wet circumstances is with the heavier loads than anticipated going over the rail lines on a much more regular basis, they jostle the track, they squeeze, or they draw moisture into the ballast underneath the track, and you get this sort of application. This is fairly extreme, but that's a large source of concern for the rail derailments. So the railways, typically what they do is they come along, they'll lift that track, they'll pack more gravel in there, rebuild the track, and it can be, they call it chronic track. It can be very expensive just to continue that process. So we've worked with CNCP, Clone Crippen, one of their primary engineers, to develop a solution that will help address this issue. And you can see it best right here. You've got a pile, it's got 2 helixes on the bottom and 1 on the top. So one of our primary things is no helixes in the frost zone. We don't want helixes in a zone where there can be frost jacking on a helix. So typically our helix is way down at the bottom of the pile below the frost zone. In this application, that top helix is designed to sit in the ballast. The ballast is designed to not heave with the frost as well. It's part of the track design. but when it hits that slumping function, what the pile doesn't touch the track, it sits just below the track, and what it does is when that surging comes from the weight of the train, it helps resist it and reduce the compression and then the drawing of water up into the ballast. So those projects, the first one was done about 3 years ago. It's still standing up well, but we continue to watch it just to make sure that it has the desired effect. But we think that there's a big opportunity in that market to assist with railroad safety. Yes?
Can I get a little more details on this mechanism from your engineers?
Yeah, absolutely. If you remind me at the end of the discussion, I'll happily. I don't think I've got the case study with me, but we have a case study on this, and we'd be happy to talk to you about it. This is a good shot of just the types of things we can do. So we can batter piles towards the installation equipment if that's what's called for, away from the installation if that's what's called for, and we've actually gone as far as straight or perfectly horizontal in a retaining wall application. We're also very good at confined spaces. So you can see here limited room to access, but with the reach of our arms, we can get into some fairly confined spaces. Some of our notable projects, we did a foundation inside of the footprint of the roller coaster in West Edmonton Mall. So again, they're putting in a new attraction. So we've done that kind of thing where you can reach over and around. It takes a little bit of planning, but our guys love those challenges. We did a walkway up in it was in the Arctic. I don't know if it was in Alaska or the Northwest Territories. We actually disassembled a tiny excavator, put it in a float plane, flew it up, and built a wooden walkway at a park. And it was interesting because they were concerned about the environment and they didn't want any disruption of the local environment. So we started at the starting point, put the piles in, built the walkway, drove the excavator out on the walkway and did the next set of piles and just built it as we went. So we never actually had to step down into the surrounding environment. The footprint was only as wide as the walkway, and the only disruption to the environment was the piles going into the ground. So quite an interesting setup. And just some thoughts on design. And again, this is an area where I have some knowledge, but not to the depth of the engineers who work in this area. So I do have a lot of friends at home who are happy to engage in the discussion. So the design of screw piles is covered in the Canadian Foundation Engineering Manual. We did contribute to the discussion around that process in 2006. So that's pretty early in the life of screw piles in Canada, or in the commercialization of screw piles in Canada. It's something that we look forward to the next edition of that manual. I think the next rewrite is in about 3 years, and so we're talking about how we will contribute to that. We think we're well positioned to really expand on what's going on. The industry's kind of grown up with these guidelines, but if you go and take a look, there's only a couple paragraphs. It's not very robust, and I think the industry's ready for more. Certainly with the expanded application, we're ready for more. We talked a little bit about the two different models, the individual bearing model and the cylindrical shear model. And which model you use depends on the spacing ratio, how much interplay there is going to be between the two helixes, and whether or not it's going to act more like two separate helixes, or whether that soil plug concept comes into play, and the soil properties, certainly the extent to which it's cohesive or cohesionless. When we do our designs, we consider both, and then we make a judgment call, a practical decision as to which to apply. We often work towards the more conservative. It's a practice. It's an uncertain world, and we want to make sure that what we do, what we put into the ground, is going to work. We don't like failures in our business. We don't have failures in our business. We've had one since I've been involved, and it was an interesting situation. We designed the piles, we put them in the ground, and they were supposed to put infrastructure on them right away. And when they had done the design, they contemplated that, and then they didn't do the infrastructure, and the pile sat. It was up in the oil sands, and the soil got wet. And for some reason, I think the install had gone down and hit a hard layer, and they stopped at the top of the hard layer. With the infrastructure on top, the piles, we think, wouldn't have lifted, but they didn't put the infrastructure on, so the piles lifted, and that was interesting to us because we hadn't seen it before. The solution for us was to put it 2 more rotations. We just moved them down 2 more rotations into the hard layer. That held it. They built the infrastructure, and so the piles didn't even have to come out of the ground. But it's always interesting to us to see that failure. Not interesting in a good way, because we typically don't have them, but always interesting when something doesn't perform as expected, because it's an opportunity for us to learn. again, the cylindrical shear method. So when we design a pile, we can estimate the torque based on the soil conditions. I'm not going into the formulas. I don't fully understand the formulas, and so I'd end up in a debate that I probably couldn't master. But there are, if anybody's interested in the design calculations, the torque estimation formulas, I'd be happy to put you in touch with the people that do this work every day. The biggest point, though, for me is that each pile that we do is special purpose designed for the use that it's going in for. And so on a large scale project, we'll have some design categories, and we use a category of pile for a category of soil. So it's not one-to-one, but everything we do is looked at by an engineer, with the exception of some of our small commercial piles. And we'll talk in a minute about the CCMC registration and sort of generally applicable piles. But there's a scientific approach to each pile design that we do. This is interesting just because of the comparison to a driven pile. So just a couple things to note. The driven pile, same diameter, 324 millimeters, 11 meters long. This pile, same diameter, but 7.5 meters long. So not quite half, but close in that range. You can see fairly similar load-bearing capacity, up to 250 kilonewtons. And then you can see the difference between a driven pile, which when a driven pile fails, it has a plunging failure and it just drops. Screw pile has a slower failure over time. So we didn't get, within the working range where our expected capacity was, we did pretty well. Once you push it to failure, you can see the different failure models. I'm not sure how relevant that is. I guess it depends. You hope never to get to that failure. Very notable, the install time, 1 hour and 16 minutes, 10 minutes. Huge difference. And that test was actually done at the Curl Oil Sands site in front of the client. So we were promoting our product. We wanted to go in and said, look, head to head, let's go in and we'll do an install test, we'll do a load test. And these were the results. So we were, when we got there, our machine, we went in, we set up, we installed our pile, we went home. We were gone by sort of 10:30 in the morning, and our friends with the driven rig were still working. And just a little bit on typical designs. One of the challenges that we see with the design of screw piles is that engineers who don't have the ability to take the theoretical knowledge and combine it with the installability knowledge tend to design piles that look funny or that can't be installed. And I don't mind how they look, but if you can't install them, they don't look very good. So typically what you'll see is you'll see kind of a small shaft and a huge helix. Right? The shaft, the torque on the shaft will destroy the shaft before that helix ever gets into the ground. That's where our structural friends are at work telling us, can we apply these forces to this pile and get it into the ground? Typically, somewhere between 2 times the shaft diameter and 3 times the shaft diameter for the helix diameter. That's a good proportional range, and it tends to work. You'll see that we come beyond 3 times the diameter in certain cases. Those cases would be very soft ground where you're looking for some level of stability in soft ground, so you know you'll be able to get it in. If there's something else going on, one of the things that we can do, we can increase the wall thickness on the pile in order to allow it to take more torque as we put a bigger helix in the ground. There might be something that drives it, whether it's equipment size, access, pile. There can be all sorts of things. So there are some creative solutions that we can come up with. But we don't do it very often. The other one that's interesting, you see a few of these under 2 times the diameter. Very hard soils are a good example of times when we would use that. So the big helixes, we just can't advance them. Sometimes we do that in the field. We'll cut off the outer inch of the helix or something like that. And because the soil is harder than expected, we calculate and determine that we'll get the expected capacity from the pile, even with the reduced helix size, because we have more bearing capacity from the soil. And I guess that's an important point, is it's important to design them with the engineers, but it's also important to install them and check your installation with engineering oversight. And that's one of the things that we do all the time. A few of the common things to think about with the design. And I'll step back and say one of the reasons that I got involved in the screw pile business is I went and looked at Almeida as a business. This is simple. This is I can understand it. You take steel, you cut the helix out of the plate, you press it into the form of a helix, you weld it on, you screw it into the ground. It's easy. At least in my mind, I can follow that through, and it makes a lot of sense. And then every time I look at a particular element of our business, I realize that it looks easy, but there are things that make it challenging. So a few of the things, the group effect of screw piles, if you get too many helices in the ground close together, they interfere with each other, and you have to start thinking about the group effect of those piles and whether that's impacting your capacity. A lot of our work is in cold weather where there's frost, and so that means that anything that happens within the frost zone is actually negative to the pile, right? The jacking force of the frost in the pile will cause it to lift. So no helixes in the frost zone. You need enough pile below the helix to counteract the uplift force and still provide the expected capacities at the surface. Anytime you're working within fill compresses and compacts over time, and it will move. So we have to look at the soils. We have to understand what the soils are, where they came from, and fill is much like frost. It operates in a different direction. It drags down, but it has that impact on the piles. Expansive soils, kind of like, again, anything in the soil that's moving, but if you get a bentonite soil, something that's going to change over time, you don't want your helix in that zone, because any force that you apply in that zone is going to move the pile. Cobbles and boulders, that's a challenge everywhere. Screw piles, when they hit rocks, it's hard to deal with. So the few of the things that we can do, we are able, in some cases, if the cobbles and boulders are small enough, to work our way around at the time of install. That works. If it's close to the surface, we can sometimes excavate, remove, and then modify the installation, go a little bit deeper, make sure that we've got the capacity that we need. And then we can move, relocate, and bridge in some circumstances as a solution. But we also find that in some cases we're just going to have to deal with it and have the ability when we hit rock to drill through it. So we're working on all of those solutions. And again, trimming the helixes. You might do that because the ground is hard, but you also might do it to taper the pile. So the smaller helix, the first helix might be a little bit smaller, and that might move a cobble, a piece of rock down there out of the way a little bit, and then the second helix could push it a little bit further. We're often asked about corrosion protection. There's many things that we can do. We can do epoxy coatings, we can do zinc-rich paint, we can galvanize, but by far the most common for us in Alberta is just sacrificial wall thickness. And so we just do a corrosion calculation and make sure that the pile is large enough to withstand the life expectancy of the project and ensure that there's enough steel there that as it corrodes, it continues to provide its expected capacity. Lateral loading is a challenge on screw piles, on driven piles, on all piles, and needs to be considered. In areas where there's no frost zone, there are treatments that you can provide at the surface, basically a set of fins that you put in that will provide more lateral loading than you would otherwise achieve, but it doesn't work in freezing soil. The biggest protection or resistance that we have, or way to overcome lateral loads, is our ability to batter those piles. So if there's a lateral force, we try to line the pile up to counteract that force in a direct plane so that it's no longer lateral. It's by far the best we can do. We have bridging techniques on the surface and that sort of thing, again, that we can use to counteract some of the lateral loads. Lots of restricted access work, low overhead, inside buildings, in tight confined spaces. Screw piles are very agile and able to come in, but what you'll find in a number of cases where there's restricted access is that the full length pile won't work. So in many cases we're doing bolted connections, shorter lengths. Maybe if it's a low overhead, you'll do them 3 feet or 5 feet at a time rather than 20 or 30 feet, those kinds of things. Always looking at the transition from the pile to the cap to the infrastructure that it's going to be supporting. And finally, that capacity to torque, that's our fundamental check on those piles. When we design a pile, we estimate the torque. If it doesn't get installed and meet the estimated torque, then you know that it won't meet the estimated capacity, and you have to revisit that design on the fly to come up with a solution that will give comfort that we can meet the expected capacity. And a few things to remember. They're economic. Screw piles are economic. they're efficient, and they're environmentally friendly. They have advantages in all of those areas, and you have to look across the useful life of a screw pile and across the project to determine how those advantages will come to bear on the project that you're working on. Versatile and able to be installed in all weather conditions, any angle. Very adaptable in their approach, and so they can be finely tuned to their application so that you can use the most efficient pile to resist the forces that are going to be applied on it in the most efficient manner. I did say we would talk about our CCMC certification, and I didn't do that on one of the prior slides, but our piles are typically custom designed for the purpose that they're intended, but we do have a Canadian Construction Materials Centre certificate for some of our smaller piles. We're expanding that from, we've got it on 2 7/8 up to 4. I think we're going to go up to 7 inches on those piles, where you have essentially a certificate that says if you install this pile to this torque, then it will support this load. And it's scientific, but it's not checked on each installation. So it's used for non-livable structures, things like decks, fences, small infrastructure, where the cost of engineering is simply prohibitive. People want to be able to just use these things. And we do it all the time. When you think about doing a deck post or a fence post, you dig a hole, you pour in a couple bags of concrete, you throw in a fence post, and away you go. Same thing with decks. There's no engineering in that. There's just kind of a standard that says if you do this, it should be fine. And the reality is that if there's a failure, it's not a critical failure. But these things are so over-designed, they ought not to fail. And that's what we see with the traditional use of CCMC certified foundations. And the last thing to remember, we're the leader in this business in Canada and in North America. So if you have questions, if you have concerns that relate to screw piles, my phone number and my email address were at the beginning of the presentation. I think, Armageddon, the presentation will be available to everybody afterwards. Is good. So feel free to look at that. Feel free to call me. Feel free to email me with any questions. We love to talk about this stuff. We love to help students and academics think about screw pile related challenges. It advances the industry, it advances the knowledge, and we think we're pretty good at it. And that's it. So I'm happy to take questions. I've also got a few, as I promised, a few individual projects that I can flash that we could just see a few of the other applications for screw piles. Yes?
So is it possible to use these piles for offshore platforms, or do you have any experience before?
Offshore platforms, I think, would be challenging. I think it'll depend on the depth of the water. But there are screw piles being used for marine applications, and we are on the cusp of that. So one of the applications that we're looking at is in Saskatchewan, where they have power lines that the water table has risen, so they now have power lines with poles in water that they can't access. So that's kind of 12 feet. So that's not very deep. And we'll access that with a floating excavator and a floating installation process. But if you get out to a marine application, we've seen application on things like fish farms and anything that anchors to the bottom, where they're anchoring infrastructure to the bottom. There's a technology coming out of New Zealand that's very good at this. They drop them in off the back of barges, and they're essentially anchors that go into the soil, and then the installation shaft is removed, and what's left is an anchor in the soil and a cable that they can attach to. So there's that application. The other application is a barge-based application. So they have an installation unit on a barge. They drop legs, and I've seen this. The water was about 30 feet deep where we saw it, and they were doing a marina. So they'd have piles in the ground. Lots of marinas on the west coast you'll see have piles that are pounded into the ground, often wood piles. A lot of them are now going to steel piles with cathodic protection systems, and they can do that off of a barge. We're going to get that at one point. You're welcome.
The bottom of your piles are open?
Yes, they are open. Typically a soil plug fills, and it would be 2 to 3 times the diameter of the pile that it blocks off.
When the friction takes over. There's no problem with you creating a tapered end closed pile.
No, you could do that.
So that, to answer Armagon's question, it should be pretty well straightforward to make your piles into shallow geothermal heat exchange piles as well.
If that's
Prefab.
prefab, it certainly could be. If there was something that, if a closed end, and that, you're right, when we talked about that, we did talk about whether you take off the 45 degree or you just put a cap inside the pile, but something to close the end is very possible. And that opens up the inside of the pile for whatever infrastructure you want in there.
The only thing will be you will have a different formula for your torque capacity relationship, because once the soil starts getting in, and if you don't allow the soil to go in, the capacities will be different. In fact, the capacities will increase.
You will take end-bearing capacity off of the diameter of the pile. I don't know how much it'll change. It'll be interesting, but
No, because the soil is not getting in,
yeah,
means the soil is getting compacted.
that's right.
That would mean that your shaft capacities will also increase. Because it depends on the properties of the soil.
It depends upon the properties of the
It depends on the. I think you're. When you get the soil plug that's in there, and it's only, you get a 30-foot pile and you get a plug that's a foot or two. The end of that, I mean, that soil has to be getting compacted as if the end of the pile was sealed at some point.
I think that about 90% of the driving is actually closed end.
I think that may be.
Because once you get that plug in that high, it's not
closed.
moving anymore. So
Yeah.
yeah.
Yeah. So and that's where the bearing capacity comes, right? It's at the bottom end of that install. So soil capacity is very important on, or soil property is very important on that. And I'm sure, well, you guys could probably sit down and figure out how it impacts better than I can, but.
He wrote a PhD about it.
Okay, well, see, I knew I could get myself into trouble if I talked for long enough with this group.
I think it's doable. I think you can put a heat exchanger pipe inside and get it to work.
When you're looking at shallow geothermal for residential or industrial applications, the big cost is always in the installation. And that's really the biggest cost, because you've got to excavate, layer pipes, heat exchange, put back on, compact, blah, blah, blah. And there is really no trenchless type technology that can be easily modified to put in, a loop. But if you have like for instance, those camp buildings that you were showing us, if you had helical piles with the bottom third being a heat exchange, in other words, maybe not the whole length, and you're putting them in maybe 15 meters deep, something like that.
Could, yeah.
Then you've got 100 piles supporting your light structure. You've got a huge thermal mass there, so huge. And because this is relatively cheap in terms of installation, if you prefab a geothermal helical pile, then you're not actually adding a lot to a lot to the cost, to the overall cost, and you're saving huge amounts of money in terms of installing a standard geothermal loop.
The other thing that you might consider is we're always trying to balance that the efficiency argument. How few piles can you use to support the load so you get in there and it's working optimally. This may change your optimization thought. You might decide that more piles and smaller are better because, and I don't know what diameters you're looking for, but you could easily use twice as many piles. It actually isn't, once you're on site, I mean, mobilizing to a site costs money, it all costs money, but you actually...
That's my point.
Yeah.
That's my point. If the piles are prefab to be shallow geothermal piles as well, the net increase in the cost of piling is very small.
It's small, yeah.
But it saves the cost of the geothermal loop installation, which is very large.
Yeah.
So that's the...
Yeah, and there may be an offset there that, and I guess my point is we might redesign the piles so that you get better optimization of the geothermal, whether it's more piles.
I think you have a proposal to them for funding a PhD student on doing the math and solving this issue in a rigorous way.
Yeah.
To some extent, I mentioned that while we talked on the phone. Right?
Well, and I'm very encouraged with our installation equipment out here and the opportunity. I think we'll be better partners than we would have been before, but I think it's very interesting.
For geothermal application, I think the corrosion method that you mentioned won't be sufficient because
well, all these.
Well, that's part of the
figure
deal.
that out.
Figure it out with the accelerated corrosion from the temperature cycling effect.
water is
But you could galvanize the piles and you'd,
Yeah, you need to add another, like,
Well, like you said, add a few more millimeters of steel over the lifespan of the.
not necessarily, but yeah.
yeah.
I agree with a coating or something.
Yeah. In Ontario, for whatever reason, most of the helical piles in Ontario are galvanized. And it's not the most cost-effective approach, but it's a typical approach.
Maybe in long term,
It depends on the life of what's on top of it.
The structure,
Yeah,
right?
yeah, that's the question.
Have you considered some kind of a hybrid pile that which will be partly maybe helical and partly like a partly screw pile and partly driven pile kind of thing, so that you can get a bigger market share of like
Drive 10 meters
Yeah,
and then screw in the last 10 meters or 5 meters so that your helixes are actually shallow
yeah.
and you've got the shaft bearing for the lower part. Would that be any efficiencies involved there?
I don't know. I've actually never thought about that.
instead of just looking for 4-story building, why can't we look for like 10-story building and partly driven, partly
See all these
Yeah.
all these new buildings here that have
Yeah.
gone up in the last 2 weeks?
Yeah. It's an interesting idea. I mean, immediately I can tell you all the reasons why it won't work, but that's always often why things don't get tried. It's a very interesting idea. You start to then think, okay, well, I need a driven rig and a screw pile rig, or a rig that can do both in order to do the install effectively. And so there's some challenges there, but I don't know that. I mean, maybe you could do it. Maybe there is such a rig, or maybe if you've got more than one rig on a project, maybe the first rig goes along and puts them in the first 10 feet, and the next rig comes along and puts the screw piles on. It could happen. I guess I'd have to understand what we thought the advantage was. And it's interesting because the helix at that point, even at the start of the helical install, needs to get traction in the soil, and it would be pushing the pile that had to be driven to that depth. Now it's going to try and push it further in rather than pulling it.
Helixes are at the bottom.
They pull. Yeah. So again, interesting. But
Because you don't want to buckle the pile.
that's right.
piles will not buckle. So
Thin wall steel, maybe.
well, they're not very thin wall.
But would it churn at the surface with the pile trying to push, right?
Yeah, there's a lot of rotational friction for the bottom part of the pile. Because your helices are at the bottom and you're
They're
screwing
cutting
in
the soil.
You tend to pull down the rest of the pile.
Why do we have to have the helices at the bottom?
That's your question.
Yeah, it's a good question.
Relatively at a shallower depth, because all you need is that torque, right? Finally,
Yeah.
add that additional.
But it also depends whether or not you have piles, like for example in very tall guide towers or wind turbines, because you have tension and compression.
Right.
And if you have tension and compression, then your helices should be lower down if possible.
It depends on the soil profile, right?
Of
It
course,
does
it
not
al-
necessarily-
it always depends on the
Yeah.
structure.
Yeah.
All right.
More questions? Nothing? So Jeff,
Okay.
on behalf of WISE and University of Waterloo, I thank you for your time and wonderful presentation. Thank you so much.
My pleasure. Thank you very much. There are, if you want to take a look at the presentation, there are a number of pictures following the question and answer slide that have sort of just project samples. Our website's available, and that video is available on YouTube. So if you just search Almita Piling on YouTube, if you want to see the video or show it to your friends or family, because it's very cool, you're welcome to do that. But thank you very much for having me. I always appreciate talking about our business and speaking with people that are interested in it. So thank you.